All right, we're good to go. So welcome everyone. This will be the first talk for the mini-conf. It's Stephen Ellis speaking about, from Red Hat, speaking about Rook and Ceph, which is a project I'm a huge fan of. I've been running at home for 2 years now on my little Kubernetes cluster. And it's a really nice solution. I'm a big fan, so I'm looking forward to this. Thank you very much.
Okay, thank you everyone for coming. It's a little tight on time. I'm effectively got 2 sets of content and a couple of demos. So we may not get through everything, but over delivery, why not? Based on the audience, I'm going to do a little bit of an intro first on Rook and what it's all about. And then I'm going to swap content and talk about a few concepts and a few things in the container storage ecosystem that hopefully will create a few light bulb moments in the room. And along the way, I'll show off hopefully a little bit of rook-ceph in action. Now, some of the content I've got here is the latest roadmap content I got off Travis, who's the main Rook maintainer. So this content has been used at some other events, but I'm going to weave a few different themes and stories around it. So what is it about Rook and Kubernetes? So what is Rook? Rook is a storage operator for Kubernetes. And Rook isn't Ceph specific. What's really nice about Rook is it's a framework for managing storage providers. rook-ceph is one, but there's a number of other providers out there. And in fact, something Travis shared recently was at KubeCon, a number of big storage vendors came up and said, how can we work better with Rook and use it to enable the delivery of our storage platforms in this Kubernetes ecosystem? But it's not just about, one nice thing is it's multifaceted. Rook allows you to install the storage technology as a container-native storage environment, as in your storage platform runs within Kubernetes and is managed by Kubernetes. It allows you to configure it natively within a Kubernetes ecosystem. But really importantly, the operator allows you to upgrade it elegantly. And often that's a big data overhead. How to elegantly upgrade a software-defined storage stack is still something that many organizations are wary of. Kubernetes, a lot of you have dealt with already. So it's a platform for distributed applications, predominantly focused around containers, but it's being broadened now into virtual machine management, serverless, and a broad range of other areas. And it has a very declarative model. You tell it what you want it to achieve, and it goes ahead and does it for you. So with storage for Kubernetes, you have these volume plugins to provide various storage backends. And these could be proprietary storage technologies from EMC, from HP, from vSAN as part of a VMware deployment, or they could be open source platforms such as Ceph, OpenEBS, etc. And the storage typically is external to the Kubernetes cluster. But one thing we're starting to see is these what we call container-native storage platforms, where the storage actually runs as a containerized service and can be managed by those kind of container-centric paradigms. Now, when you're running your container platform up on a public cloud, you may be just consuming cloud-based storage, Amazon S3, EBS, and equivalent technologies from the Google and Microsoft cloud platforms. Now, I'm not going to go through this in detail. It's in here for kind of reference, but some of these terms may come up. Custom resource definitions are really critical to our ability to extend Kubernetes and provide capabilities above and beyond anything the original Kubernetes developers would have thought possible. Operators are a relatively new addition. They came out of the CoreOS team as a way to encapsulate a lot of operational tasks and automate them in a way that makes your container environment even more hands-off. A PVC, a persistent volume claim, is fairly critical. That's the storage that we're attaching to a pod or a containerized workload. And CSI is the container storage interface. This is really key going forward as the main way we're going to be plugging third-party storage platforms into a Kubernetes ecosystem. And these 3 terms are very critical when we're talking about how storage is consumed by Kubernetes applications or containerized applications. So read-write once, it's being attached to and read-write mode to a single node or a single container. ROX, read-only many. Think of it like just mounting a read-only file system. Because it's in read-only mode, we can elegantly attach that to many containers. Read-write many is often the hard nut to crack. It's a hard one to deal with, and a lot of people default to NFS for that, which has some interesting pain points and idiosyncrasies. I can't quite say it, but there's issues, right? There's pain points, and I'll cover that why in a moment. So I'm going to just swap content here because this is something I've been using to explain why in a containerized ecosystem we need dynamic storage. Because many of us were dealing with workloads traditionally, in a virtual environment or in a physical environment, are used to storage being a large overhead. You've got to go and tap the storage admin and have them do something for you. It's not something that can happen dynamically and rapidly. As we're moving into cloud ecosystems, we're used to having cloud APIs to do this for us, but how elegant and how rapid are they? And how efficient are they? So in the past, now in this case I've shown Red Hat Virtualization and Red Hat OpenStack because that's where I work, but this could just as easily be any other hypervisor platform, any other implementation of OpenStack. You've got a Kubernetes cluster, some masters, some nodes, and under the hood they're consuming a broad range of storage from a variety of providers. What I don't show here are actually kind of your traditional providers. It could be iSCSI, Fiber Channel, NFS as well. And the key person is operations is kind of the safeguard to this, and I've got to let them know in advance that I want some iSCSI endpoints defined. I want some Fiber Channel LUNs. I want some NFS exports set up. But if I'm using the cloud APIs, I can do some of this dynamically. But there's a degree of overhead, of busy work, of trying to manage this. So what happens then is your operations team says, I'm going to pre-allocate you a whole bunch of storage, and I'm going to allocate that to your container farm. So I've got a bunch of 1 gig endpoints, 5 gig, 10 gig, allocated off my iSCSI SAN. And the developer comes in and builds an application. It requests 10 gig, it gets allocated, my application comes up, I'm all good to go. A new developer builds an application, they also want 10 gig, that's awesome. We're all good, we're running 2 workloads. And then we have a problem because the third developer wants a 10 gig endpoint, and we've run out of those. And the storage backend has no way of dynamically resizing those 2 5s into a 10. Everything's been pre-allocated. Now, often in early application development and in pilots and POCs, this is how I'm seeing an awful lot of containerized environments being built, because they tend to size them enough to do the pilot, the POC, but then they don't size them for real-world workloads. Now, one thing is that your workload finishes, the storage gets deallocated, but it doesn't get recycled because the backend has no way of telling the storage infrastructure to delete the data and to reclaim that storage and make it available. Same thing happens if you're using things like NFS. You may have allocated an NFS endpoint, you've allocated it to your container, and when it gets disposed of, that data still lives on that NFS endpoint unless you've got a script, some busy work, or a third-party tool that can go in and deallocate that storage and then tell the environment's available for reuse if you're dealing with this in a static context. And it's surprising how many places still work this way because it's easy. It's very easy to do. If I'm doing a quick hack, I just go and allocate some storage, use it, I'm good to go, and I throw the environment away. So in this case, we still have a problem because ops has got to go in and do some busy work again and clean things up. If we have a dynamic storage platform, doesn't matter what the dynamic provider is, but if it's truly dynamic, things change. And the idea here is a container-native storage environment's agnostic to the infrastructure. You talk to it, it deals with all the heavy lifting, all the busy work. So in this case, I've got the same amount of storage. I've got my 34 gig, but it's not pre-zoned, it's not pre-allocated. I've just said, give me some storage. And then operations is hands-off. They don't do anything. The developer, the storage provider, everything is automagic. Everything happens dynamically. I want 10, I want another 10, I want another 10. An application finishes, the workload dies, the storage gets reclaimed. We're living in a proper, true dynamic ecosystem, and then new applications can be deployed. The watermark goes up and down. Now, if we're dealing with this in a proper environment where we've got build pipelines and we've got triggers running off our Git repository. Try animating this in Google. It's interesting, right? But here we go. We've got an application pod. It runs, it gets mounted. We get a new application workload because we're running off triggers. I'm completely hands-off here. All of this is happening thanks to Git Commits. Isn't this awesome? Hooray! And then things happen. Then a workload comes to its natural end. We get the deprovisioning, we get the release, and so forth. Things are hands-off. Things are nice and clean. This is the way we should work in a true container ecosystem. All the heavy lifting is being done through automation, through operators. And that's one of the goals of things like Rook. Once it's installed, not only will it install the storage for you, it will do all the data operations. So hopefully that makes sense. That sets kind of the context. Now, what I'm going to do here is I actually have, because I work at Red Hat, OpenShift is our primary Kubernetes platform. You can go and play with OKD, which is our upstream version. That's our upstream that sits between Kubernetes. Think of it as like our Fedora for Kubernetes, OKD. And I've got two different OpenShift environments here. So this one has currently no persistent storage defined. It's a whole new environment. But I have installed the operators for managing this. So I can now go and create a storage cluster while I tell you about Rook. Because this will take a few minutes. Because what it's going to do, because this is running on Amazon, is it's actually going to go and tell Amazon to give me a bunch of EBS disks. Now you say, well, why don't I just use EBS natively? EBS, if you make a request, may take 3 to 5 minutes-ish sometimes to provision. If I'm doing it with OCS, with OpenShift container storage based on Rook and Ceph, or I'm just using rook-ceph natively, the turnaround time is maybe a second or two. When you've got a large number of build pipelines, that's really critical. If you're doing an awful lot of work through your containerized platform, you've got an awful lot of triggers, those latencies really matter. Also, EBS isn't multi-AZ. We can actually go and pull 3 pools of storage across different AZs and combine them into a single Ceph cluster, which is what's going to happen here. So I'm going to go into operators, installed operators, and just OpenShift and find the storage operator. Now I'm going to go and create a storage cluster. Now I've got a bunch of nodes, Kubernetes workers and masters deployed here. I just need to make sure I pick up the right ones. So I ran this earlier, so I want 141.30, because these are all labeled, so I can find the right ones. 204 and 170. So they're all in, as you can see, I've got one in 1C, 1A, 1B. So I'm going to do this multi-AZ. I hit create. That's it. I'm now hands off. Behind the scenes, Rook's gone away. It's going to do a whole load of busy work. So if I actually now go and do where have I got it? Find the So right now, it's already starting to kick off the generation of all the containers associated with this. And as it runs, you'll see these canary mons appear. It will actually tell AWS under the hood to give me the EBS storage. It will attach that dynamically to the pods providing the storage. It will build the actual Ceph cluster under the hood, and then that will now be available as storage classes for my applications to consume. That's going to take about 5 minutes. And if you want to resize it, you just tell it to go and create some more storage pools, and off it will go. And in 5 minutes, I've got yet more storage I can consume natively by my applications. And my developers don't care. My pipelines don't care, as long as they know what the storage classes are. So while that's running, we'll talk a bit more about Rook. So I've kind of covered some of this already. Operators codify the way to deploy and manage an application and achieve a certain desired state. And then the Rook architecture, well, Rook owns the management of Ceph. Ceph CSI is the CSI driver that actually does the provisioning connections. And then Ceph offers you these the capabilities for block, file, and object, which then translate into those RWX, RWO primitives that we mentioned earlier. And under the hood, as you can see, we end up with quite a bunch of different containers. The way it works is that for every block device we attach into the pod, we get connect into a given worker node. In Kubernetes context, we get a Ceph OSD container started. So each block of storage has its own Ceph instance, Ceph OSD attached. And then we have some Ceph Mons and other services running and fully distributed and highly available. And it means that with Rook, we can actually manage the upgrades elegantly as well. And then when the applications are running, they will make a claim, they will go down to the storage class, and then it will all be handled automatically for you. And it's all being allocated of an underlying distributed Ceph cluster that you can then scale out as your environment grows and your needs change. Some recent features, so upgrading the daemons one at a time, waiting for the environment to reconcile. This is really critical. Whether you're dealing with software-defined storage on physical or virtual or containerized environments, make sure your data is consistent before you upgrade the next node. If you don't get consistency, you've got a problem. Well, one of the nice things with Rook as an operator is we can make sure the environment's consistent before we upgrade the next member of the farm. So the CSI driver is now the default way we do Rook. There was a Flex driver that we used historically, so that's the default going forward. We now have object bucket provisioning. I'm not going to go into that in a lot of detail because we're a bit short on time. One nice thing that's coming forward is the ability to use external Ceph clusters as well as Ceph native to the containerized environment. Well, let's see. So that looks like it's all running. And then, topology awareness is doing things like, spreading your monitors out. Think about it in terms of making sure I can suffer a full AZ failure and making sure that all the services are truly distributed when you're working within a cloud context. But we're working on making this topology awareness feed down into other platforms. So within OpenStack or whether we're running on VMware, we can make sure that you can set in a topology awareness so you can lose a hypervisor or lose a rack and the environment will still maintain availability. What else? Now, new features. There's a new crash dump collector come in, and there's a whole bunch of other features coming in the roadmap. So we're running low on time, but there's a few other things we'll cover off. I'll kind of skip that. What we'll actually do is jump to more of the demo. So if I come back up here to the dashboards, I've now got a storage cluster with some visibility here through this particular dashboard. What I've also done, because I've got some scripting, hang on, it's not quite up. No, so I've got a problem with that one, so here's one I prepared earlier. It's a different, I've got two clusters running here. So this I can actually run a Ceph toolbox container and run a shell into it. I can actually do standard Ceph management tasks in here. But one thing to understand that's really critical to this is through the Rook interface into Ceph, we're not making all of the knobs available, all the bits you want to twiddle if you're a regular Ceph administrator, because there's a lot of them. Andrew, is there a lot?
Yes.
Yeah. So what we want to do is make it as simple as possible for you to quickly set up and consume a container native storage footprint. And you can just do this straight out the bat with fully upstream Rook. You go to rook.io, there's a quick walkthrough, and like in 5 minutes on your Kubernetes cluster, you can have a highly available storage cluster running. Now, the other thing here is, why is this important? So quite often, yeah, I'm out of time, so I'm going to just overrun a moment. This is a simple file application deployed. This is currently running in a, let me log out of this. This is currently running in a 3 container configuration for high availability. So if I upload a file, random file, into this with a standard container configuration, and I go and list uploaded files, there it is. If I just go and run this will actually go and do an LS inside all 3 pods, and you'll see that the actual file only exists in 1 pod because I don't have shared storage between them. And because this is a file-based backend, I really need an RWX type storage footprint. Now, often this will be something like NFS. But with container native storage, I can just tell it to go and change its storage class over to our new storage. So I'm going to just make this change. Yes. By simply changing the storage class, those containers will redeploy. I will now have a common RWX backend between the 3 containers, and if I upload a file now, and I do the same LS, I'll see the same file in all 3 because it's effectively using the same backend. If I then go and look inside Ceph, I'll see that there's been a PV created and a PVC allocated, and the storage is being consumed actually off CephFS. Because when we do RWX, it goes backends onto CephFS, whereas when we're doing block, we're just backing onto straight Librados. Hope that makes sense. So I'll show that off in a minute, but are there any questions? Because we need to wrap up shortly.
Yeah, any questions now or later on? Yep. Yeah, we are. It's coming.
We are on the line. So I'm just creating the last. So because of the change of the definition of the pods are being recreated. So this will be back up and running in a moment.
Have you used Rook in production, and for how long, and do you have any issues with this one?
So for some of the big events we've been running in the region recently, we actually ran it all on top of Ceph Rook. And those environments were running for several months. This is stuff that's relatively new. We've got a bunch of customers regionally and globally on the early adopter program for this because we are commercial GA of it's about to go live. But I know Travis knows people using this in active production today off the community branches. And at least with the community branch as well, there are stable releases that you can tag against, so you're running against the 1.1 or 1.2 release. Where it gets really interesting is when things randomly go down or you don't fully clean up after certain workloads have gone away. If any of you work with Kubernetes at scale, it's great if you want to scale your workers up, but dynamically scaling your workers down can cause some interesting havoc if you don't actually evacuate them properly, and that can cause some issues if you think there's like a pod running on a worker that we've now decommissioned that may still think it's got some storage attached. So sometimes you've got to go and do a bit of magic to tidy things up under the hood. Otherwise, things can get a little funky, but by and large, it's pretty solid and stable at the moment. Okay, so that's up and running. The file has gone because this is a whole new environment. Upload the same file. Any more questions?
Yeah, we're out of time pretty much, so I'm afraid.
Okay.
Catch you out in the hallway.
All right, yeah, so catch me out in the hallway because we're going to be doing the job spoff in here any minute now. So thank you for your time.
Thanks very much. What time's that now? So see you back here at 1:30.